Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper 4 exam for May-June 2017 variant 1. So let's get started. Question 1 says figure 1.1 is the speed time graph for an ice skater. Part A says explain what is meant by deceleration. It is the rate of decrease in velocity. Part B says use figure 1.1 to determine first the distance traveled between time 3 seconds and 6 seconds. The distance from a speed time graph can be found by calculating the area under the graph. So starting from 3 seconds and ending at 6 seconds, this is the end of the part we need and this is the start. The area here looks like a trapezium and the first base is 11, the second base here is 5, and we have the height from 3 to 6 to make the area of the trapezium here looking like this is 3 from 3 to 6. First we say that the distance is equal to the area under the graph and then we substitute the average base 11 plus 5 divided by 2 multiplied by the height 3. That gives an answer of 24 meters. Double I says the deceleration between times 3 and 6 is required. We can calculate the acceleration, which is equal to the gradient of the graph, and we can use the same points. We had at 3 at x-axis, 11 on the y-axis, and for 6 on the x-axis, we have 5 on the y-axis. So using these points, 5 minus 11, y2 minus y1, over 6 minus 3, x2 minus x1. This gives an answer of -2. So if the acceleration is -2, the deceleration is 2 or 2.0, and the unit is meters per second squared. Part CI says state what happens to the size of the deceleration after time 6 seconds. In the graph after time 6 seconds, it began to curve like this. So this is a decreasing gradient. So we say the deceleration decreases as the gradient decreases. And state what happens to the resultant force on the skater. The resultant force is proportional to the acceleration or deceleration according to F is equal to ma. So as A decreases, the resultant force decreases. So we say here it decreased or decreases. Question 2 says a footballer kicks a ball vertically upwards. Initially the ball is stationary. His boot is in contact with the ball for 0.050 seconds and the average resultant force on the ball during this time is 180 newtons. The ball leaves his foot at 20 meters per second. Calculate first the impulse of the force acting on the ball. The impulse is calculated either force multiplied by time or is equal to the change in momentum, mass times change in velocity. But the mass was not given in the question, so we used this part of the equation. The force was 180 newtons and the time was equal to 0.050 seconds. This gives an answer of 9.0 newtons second. Or we can use another unit, kilograms meters per second. Part double I requires the mass of the ball. Now we can use the other part of the equation. The impulse is equal to mass multiplied by the change in velocity, and the momentum changed by a value of 9, or the impulse was 9. The mass is unknown. The final velocity of the ball was 20 and the initial was 0. So dividing by 20 on the other side, we get a mass of 0.45 kilogram. Triple I says calculate the height to which the ball rises and ignore air resistance. If air resistance is ignored, we can either use the energy and say that the initial kinetic energy is equal to the final gravitational potential energy and substitute with half mv squared for kinetic and mgh for potential. The mass will be cancelled out, so we have half times the speed 20 meters per second squared is equal to g, which is 9.8 multiplied by the unknown height, and then we divide by 9.8. Another method is to use kinematics, and we say that the final velocity at the maximum height is 0. Initial velocity from the foot of the player is 20 meters per second, and the acceleration is equal to negative 9.8, gravity acceleration, but downwards. And we need to know the final displacement, or the distance, and we use v squared is equal to u squared plus 2as. Substituting, we have 0 is equal to 20 squared minus 2 times 9.8 times the unknown distance s or h. Both methods will give a height of 20.408, so we can approximate that to 20 meters. Part B says while the boot is in contact with the ball is no longer spherical. That means that it changed shape. State the word used to describe the energy stored in the ball due to deformation. That would be strain energy or elastic energy. Question 3 says figure 3.1 shows remote sensing equipment on the surface of a distant planet. The mass of the equipment is 350 kilograms and the acceleration of free fall on the surface of this planet is 7.5 meters per second squared. State what is meant by the term weight. It is the force of attraction due to mass and a gravitational field, or a gravitational field acting on a mass. Double I says calculate the weight of the equipment on the planet. The weight is equal to the mass multiplied by the gravity field strength. So we have the mass given in the question as 350 kilograms, and the value for G here is not 9.8, it is 7.5. This gives an answer of 2625. We can approximate that to 2600 newtons. Part B says the equipment releases a balloon from a point that is a small distance above the surface of the planet. The atmosphere at the surface of this planet has a density of 0.35 kilograms per meter cubed. The inflated balloon has a mass of 80 grams and a volume of 0.30 meters cubed. Make an appropriate calculation and then predict and explain the direction of any motion of the balloon, whether it falls or it rises or floats. Show your working. First, we need to know the density of the balloon, so we divide mass by volume. But since the original density of the atmosphere was given in kilograms per meter cubed, we need these values also to be in kilograms and meter cubed. So we convert 80 to kilograms by dividing by 1000, and the volume was already given in meters cubed. This gives an answer of 0.27 kilograms per meter cubed, which is less than the density of the atmosphere. So the prediction is that it goes upwards, and the explanation is that the balloon is less dense than the atmosphere of the planet at this point. Question 4a says a 240 volt 60 watt lamp is connected to a 240 volt supply, so the power emitted is 60 watts. The lamp has a constant temperature. State the rate at which the lamp transfers energy to the surroundings. Rate of energy means energy over time, and energy over time is equal to the power, so we use the number with the unit for power, which is 60 watts, or we can say that the unit is joules per second for a rate. Double I says the names of the thermal process by which the lamp transfers energy to the surroundings. Actually, it can transfer energy by all means of energy transfer. Conduction, because it must touch something to be held in place. Convection, because the air around the lamp will get hot and rise and colder air will replace it. And radiation, because all objects with higher temperature than the surroundings emit radiation to the surroundings. Part B says figure 4.1 shows a thick copper block that has been heated to 400 degrees Celsius. One side of the block is dull black and the other side of the block is polished and shiny. In experiment 1, the thermometer bulbs are both painted black. They are placed at equal distances from the surfaces of the block. The maximum temperature shown by each thermometer is recorded. So heat radiation is given to the thermometers from the block because the block itself is the hot object. So we are talking about emission of heat radiation to the thermometers, but one surface was dull black and the other surface was shiny. Explain any difference between the maximum temperature shown by the two thermometers. So the one next to the black side will show a higher temperature because black is a better emitter of infrared radiation. So this is the answer. We say thermometer A on the left side shows higher temperature since black surfaces are better emitters of infrared radiation than shiny surfaces. Double I says in experiment 2 the thermometer bulbs are both painted shiny silver colored. They are placed at the same distances from the surfaces of the block as in experiment 1. So we have the same experiment, but instead of using black thermometers we used silver or shiny thermometers. State and explain any differences that are observed in the maximum temperatures now. We say that thermometer A still shows a higher temperature due to the explanation we said in the previous question, but both thermometers will now show lower temperatures since they will receive less radiation because shiny surfaces are poor absorbers of infrared radiation. So we receive less heat, the temperature we reach is lower. Question C says figure 4.2 shows a firefighter wearing shiny silver colored clothing. State the benefit to a firefighter of wearing shiny silver colored clothing. We say that it reflects heat radiation to prevent skin burns or any damage to the body inside the suit. Question 5 says figure 5.1 shows some gas trapped in a metal cylinder by a piston. A says the position of the piston is fixed and the cylinder is moved from a cold room to a warm room so the temperature increases. Explain in terms of molecules what happens to the pressure of the gas in the cylinder. We start by saying that as temperature increases, molecules gain kinetic energy and collide harder or with greater momentum and more frequently with the walls of the cylinder, exerting greater force on the walls area, so the pressure in the cylinder increases or gets higher. Part B says the piston is now released, it moves to the right and finally stops. Explain these observations in terms of the pressure and the volume of the gas in the cylinder. So first we say that the pressure inside was greater than outside. That caused the piston to move, and as volume increases, the pressure decreases because they are inversely proportional until the pressure inside is equal to outside the cylinder, and now there is no resultant force to push the piston, so it stops. Question 6a says a ray of light in glass is incident on a boundary with air. State what happens to the ray when the angle of incidence of the ray is less than the critical angle of the glass. So going from glass to air, we bend away from the normal. So we say it refracts from normal and speeds up. For double I, we say greater than the critical angle of the glass. We say that what happens is total internal reflection because we are moving from a denser medium to a less dense medium with an angle greater than the critical. B says figure 6.1 shows a ray of light incident on a glass block at A. The critical angle of the glass is 41 degrees. On figure 6.1, without calculation, continue the ray from point B until it leaves the glass. Here we need to know the angle of incidence between the normal and the ray. So we subtract 30 from 90, that gives us 60 degrees. So the ray will actually be totally internally reflected because the angle 60 is greater than 41, the critical angle. So now we sketch a ray which is at the same angle as the incidence towards the end of the block, and leaving the block we have the normal like this, 90 degrees on the surface of the block. You should draw it with a protractor, and since the angle of reflection is also 60 and this angle is 90, this angle is 30, which is less than the critical angle. So this time the ray of light will go out of the glass block, but since we are moving from glass to air, it will speed up and bend away from the normal, and we label the direction of the flow of light. We are not required to label anything on the rays except for the direction. Double I says calculate the refractive index of the glass. We can use the critical angle and say that n is equal to 1 over sine the critical angle. So 1 over sine the angle 41 given in the question. This gives a value of 1.52425. We can approximate that to 1.5, and the refractive index has no units. Question 7 says a loudspeaker produces a sound wave of constant frequency. State what is meant by frequency. It is the number of oscillations per unit time or per second. Part B says a sound wave travels in air towards a barrier with a small gap at its center. Figure 7.1 represents the compressions of the wave traveling towards a barrier. State what is meant by a compression. We say that particles are close to each other and have high pressure or cause high pressure. Double I says the width of the gap is smaller than the wavelength lambda of the wave. On figure 7.1, draw the pattern of the compressions after the sound wave has passed through the gap. So passing through a gap like this will cause circular diffraction. First, we need a ruler to measure the distance between the wavefronts and continue the direction of travel of the wave. So if you continue this line horizontally, and the distance between each wavefront and the next is 1 centimeter, we label equal distances. 1 centimeter apart on the other side to get the position of the diffracted waves. Now we use a compass and we place the center of the compass at the last wavefront that did not pass the barrier. So the edge of the compass is at this point. And then we use the compass to draw the curved sections. So going like this. It's not an exact diagram, but you should draw it exactly. Now we increase the length and draw the next one. From the next point, we draw a curve that is slightly wider like this. And then we go to the third point and draw this third curve, which is wider again. So this is the final shape of the diffracted wave. Triple I says the barrier is adjusted so that the gap becomes wider. Describe how this affects the pattern of the compressions after the sound wave has passed through the gap. We say that it will be less curved and there will be less spreading of the wave. Part C says the frequency of the sound wave is 6800 Hz. The speed of the sound in air is 340 meters per second. Calculate the wavelength. The wavelength is equal to speed divided by the frequency. We have the speed 340 and the frequency 6800. That gives an answer of 0.050 meter. Double I says state a typical value for the speed of sound in a liquid. Like water, it would be 1500 meters per second. You should remember this. Question 8 says a bar magnet is made of a metal. Suggest a metal from which the bar magnet is made. It must be a hard magnetic material like steel, so it can become a permanent magnet. Part B says figure 8.1 shows the bar magnet being inserted into a coil of wire. The N pole and the S pole of the bar magnet are marked. The coil is connected to a galvanometer. Explain why the galvanometer deflects as the bar magnet is being inserted into the coil. We can say that as the magnet moves, it creates a change in flux or change in magnetic field. We can also say that its magnetic field cuts the coil. So we say here change in flux in the coil, and this induces an EMF across the coil. So there is a current going through the galvanometer. Double I says explain what determines the direction of the reading on the galvanometer, which is the direction of the current. We say the direction of motion and which pole of the magnet is facing the coil. If you reverse the polarity of the magnet, the direction of the current induced will also be reversed. Question C says describe a method for demagnetizing a bar magnet. We can say pass the bar slowly through and out of a coil or a solenoid connected to an AC or alternating current power supply. Question 9a says the resistance of a circuit component varies with brightness of light falling on its surface. State the name of the component. It is a light dependent resistor. Double I says draw the symbol of this component. It is a rectangle like a resistor with two arrows falling on its surface. Part B says figure 9.1 shows a 6-volt battery connected in series with a 1.2 kilo ohm resistor and a thermistor. At a certain temperature, the resistance of the thermistor is 2.4 kilo ohms. Calculate the reading on the voltmeter. We can use cross multiplication and say that if 6 volts are given to 1.2 plus 2.4 kilo ohms, how many volts are given to the 2.4 kilo ohm resistance of the thermistor alone? 1.2 plus 2.4, that is 3.6, so we multiply 2.4 times 6 and then we divide that by 3.6 to get the voltage. This gives an answer of 4.0 volts. Another way of solving this question is getting the current. The current is equal to the total voltage over total resistance. So 6 divided by 3.6 times 10 to the power of 3 for kilo ohms. And then substituting in V equals IR, we got the current and we have the resistance of the thermistor, 2.4 times 10 to the power of 3. We will get the same value for the volt. Double I says the battery connected to the circuit in figure 9.1 is not changed. Suggest a change that would cause the reading on the voltmeter to decrease. So this circuit is a potential divider. We need the voltage here to decrease. This means that the resistance here decreases or on the upper side increases, but this is a fixed resistor, so no change happens here. This resistance now must decrease. And the resistance of a thermistor decreases when the temperature increases or there is a rise in temperature. Question 10a says describe the movement of charge that causes an object to become positively charged. We say that there will be a loss of electrons or removing electrons. B says figure 10.1 shows a negatively charged rod held over an uncharged metal sphere. It has free electrons inside. On figure 10.1, add positive and negative signs to represent the results of the movement of charge within the sphere. So the negative charge in the rod repels the free electrons downwards and leaves the upper side of the sphere positively charged with protons without their neutralizing electrons. But we must make sure that the number of negative signs drawn is equal to the number of positive signs drawn. Double I says describe the actions that must be taken to attain an even distribution of positive charge on the surface of the sphere. So this is charging by induction. We already brought a negatively charged rod near the metal. Next we need to connect the sphere, which is the metal here, to ground or earth momentarily, which means connect and then disconnect, then remove the negative rod. When you connect the sphere to Earth, it will see that the total negative charge in the whole system, the sphere and the rod, is more than the positive charge, so it will remove electrons from the sphere, making it positively charged. But to make sure that the electrons removed do not go back to the sphere, we remove the Earth connection, and then we remove the rod to make the free electrons in the sphere move freely and distribute the charge evenly. Question 11a says radioactive source is tested over a number of hours with a radiation detector. The readings are shown in table 11.1. Use the readings to suggest a value for the background count rate during the test and to determine the half-life of the sample. To get the average background, we see if the numbers fall and then rise and keep falling and rising around a certain number. So starting from here, the readings keep falling and rising again. So we calculate the average from here, 21 plus 17 plus 21 plus 20 plus 19 plus 20 plus 18. And then we divide by the number. These are 7 readings, so we divide by 7. This is approximately 20. It's 19 point something, so approximately 20. Now to get the half-life, we take the first reading and subtract the background. 324 minus 20, that gives us 304. If we divide that by 2 to get the final activity after one half-life, 304 over 2 gives an answer of 152. If we add the background plus 20 to get the reading on the table, that gives us 172, which is not in the table. So we go another half-life, 152, which is here, divided by 2 again. That gives us a value of 76. Again, we add background and check if the number is in the table. That gives a value of 96. It is in the table, and after 1 hour, but we've passed 2 half-lives. So if 2 half-lives take up 1 hour, then the half-life is actually half an hour or 30 minutes, and the background radiation was 20. Part B says hydrogen-3 tritium has 1 proton and 2 neutrons. The nucleon number for tritium is 3. It decays by emitting a beta particle. Complete the nuclide equation to show this decay, and the symbol X represents the nuclide produced by this decay. Now from the question, the nucleon number for the tritium is 3, and we have 1 proton, so the proton number is 1. For beta, you must memorize it is 0 and -1, which means 3 minus 0, we get 3 for X at the top, and at the bottom, we have to make this 2, so that 2 minus 1 is equal to 1. Part C says the arrows in figure 11.1 shows the path of 3 alpha particles moving towards gold nuclei in a tin foil. On figure 11.1, complete the path of the 3 alpha particles. So the one that is going directly towards a nucleus rebounds backwards. The one that is going close to a nucleus gets repelled away, like this. And the one moving away or far from the nuclei keeps moving forward in a straight line. So this was the end of the exam. I hope you enjoyed this video and found it useful to you. Keep practicing, and I will see you in another video.